This presentation is delivered by the Stanford Center for Professional Development.
Okay, hi everyone. Okay, so today will be the last class doing statistical parsing, and so today there are three topics I want to cover. The first one is to look in more general at other ways that you can do the parsing task, which are effectively different ways of doing this search task of finding good parsers. Then I want to say something about dependency grammars and how they contrast with doing the kind of constituent grammar parsing that we've mainly concentrated on. And then just at the end, I want to say a teeny little bit about using discriminative methods in parsing. I'm not going to cover that in very much detail, but just to motivate the idea as to why it's a useful thing to do, say a fraction about how people do it, and tell you about a couple of results using discriminative parsing. Okay, so right at the end of last time, I mentioned these goals of what you might want to do with a PCFG, and how particularly if you just want to find the best parse for a sentence, that rather than doing CKY as we've done up until now, that maybe there are clever search techniques that you'd like to employ which might work better. And two methods you could use are beam search, and that's certainly been used quite a bit for parsing, just like MT, but I'm not going to talk about that now. And then this idea of a gender chart-based search. Okay, so just going back a little to the fundamentals. So what do we have? So for what we've built for parsers, we have items, which are commonly in the older literature also called edges, but they'll be confusing, so don't think edges, because these are really going to be our nodes. So these are items that are things that we can build over a span. So that's something like a noun phrase between position 0 and 2. And then we have backtraces or traversals, which they represent the way in which you can make something over a span. So the backtrace or traversal is this red bit down the bottom, and it's recording that the way I was able to make this item, a sentence from 0 to 3, was combining a noun phrase from 0 to 2 and a verb from position 2 to verb phrase from position 2 to 3. Okay, so then you can think of a parse tree that you get out at the end as a collection of the items that you build and then the traversals that they're built from. So a parse tree is a representation of that sort. And in general, when we're exploring possible parse trees, we're building some kind of packed representation in which we can record a whole lot of partial hypotheses. And the parts of those partial hypotheses are things of that sort as well. And so the main thing that we've done so far is use this idea of a parse triangle or chart representation for CKY parsing. And what we did as an organizational concept there is that we took all things that were items over the same span and put them in one place. So that here, if we have both a verb phrase and a verb from position 2 to 3, and the word ran from position 2 to 3, that all of these things would be stored in the same cell as things over the same span. But if we think in general about this picture of having items and traversals, we can just sort of draw all of our items, and then we can draw traversals that can construct different items. And what we want to do is search in this space where we can gradually start building different ways in which we can build new items by making a traversal that combines two different things. And so if you do this in the general case, the data structure you get is a B-directed hypergraph, which is a kind of a cool data structure. So there's this general concept of hypergraphs, where in hypergraphs, unlike the regular graphs that you normally see in computer science, in hypergraphs you have nodes just like before, but the edges between nodes can have any number of tails and any number of heads. But the whole assemblage of those things counts as a single edge. And so, for example, this here is a single hyperedge where you're making a sentence headed by payrolls out of these two pieces. So particularly for the case of parsing, where we have these binarized trees, the situation that we have is that our hyperedges have at most two tails and always have one head. And hypergraphs with that form are referred to as B hypergraphs because they have this binary nature, and B hypergraphs have special properties because they can be processed more efficiently than general hypergraphs. And so they're directed. You can also have undirected hypergraphs, but these are directed hypergraphs, of course, saying that from a pair of things, you can then deduce a bigger thing. So that if you've built a preposition from 3 to 4 and a noun from 4 to 5, then you can traverse this hyperedge and build a prepositional phrase from positions 3 to 5. So in the general case, what we want to do is search, which is sort of like search that you can do in other contexts in AI. Apart from here, we're doing search in hypergraphs rather than in regular graphs. Okay. So if we think about that, we can then think, well, surely there are other ways in which we can do search inside this hypergraph. And well, what do we do if we do CKY parsing? Well, in CKY parsing, you know, this is a hypergraph, right? Because I've got these hyperedges here that connect up two things and rewrite them as another thing. All I've done with CKY parsing is I've kind of organized the hypergraph into a certain shape. I've kind of piled all of the items that cover the same span on top of each other, and then I've imposed by my dynamic programming algorithm a certain order of exploration. So what I do is I first of all build everything that I possibly can over spans of size 1. I then build everything I possibly can over spans of size 2, everything I can over spans of size 3, and I get up to eventually finding parsers of the sentence. Now, the good thing about this algorithm is it's really simple to write as a dynamic program. Well, that's one good thing about it. I hope you found that when you're doing the assignment. The second good thing about it is, you know, it's kind of trivial that this algorithm is correct. You can't really kind of mess up the correctness of it because you just build everything small, and then once you've built smaller things, you build larger things on top of it. But the bad thing about it is, well, what we actually want to build is items that span the entire sentence. And by the construction of the algorithm, we're going to attempt to build absolutely everything possible that has a smaller span before we even attempt to see whether there are constituents that span the whole sentence. And that seems kind of bad because, I mean, probably some of the things that we're building down here were really, really unlikely. So surely there must be some way to do a cleverer search exploration so that we don't build all of those candidates. And there are, and people have explored that quite a bit in parsing. And the obvious idea there is that what we're going to use is that we're going to use in some way the probabilities, the scores of items to decide what are promising hypotheses to pursue and which things aren't promising hypotheses to pursue. And that leads into the idea of agenda-based parsing. So for agenda-based parsing, we have the same kind of table recording scores of things over span. So the table looks just like the kind of table that we use for CKY parsing. But in addition to that, we're then also going to introduce an agenda as a way to order our search. Okay, so we start with this table like before, and we put in words, and we give the words their scores of having different parts of speech. Okay, but then on top of this, that we're going to introduce a second data structure, the agenda, and the agenda is going to be items of the same sort, actually. It's going to be something like having a noun phrase between 2 and 3, but it's also going to have a score attached to it. And we're going to, and the score is in some way connected with the probability of things. I'll explain the details of that later. And what the agenda is going to be is some sort of priority queue so that we can decide what to work on next based on its score in the agenda. Okay. And so we're gradually going to build up things in the chart, and if we find better ways of making things in the chart, we'll then lower the score of the corresponding thing in the agenda. And so the idea is that the agenda will tell us what to work on next that's the most promising thing. Okay, so we have this kind of two-way communication between the agenda and the chart. So what we do is we will build things in the chart, and when we found a new way of building something, like I found a new way of building a noun phrase from words 2 to 5, that will then go as a thing to work on the agenda. And the agenda will be ordered, and if it gets to the top of the agenda saying that one of the most promising things I found is noun phrases from 2 to 5, it will then come off the top of the agenda, and then we'll explore ways to search further, such as, if there's a noun phrase from 2 to 5, maybe, and we have a rule of noun phrase goes to noun phrase prepositional phrase, so therefore we could build a new edge of noun phrase from 2 to 10, say, because we know there's a prepositional phrase further to the right. So that will then generate a new edge that will go into the chart, and then immediately that will lead to a new thing being put on the agenda, which is at some point you should then explore that new noun phrase from 2 to 10 and work out how you could build even bigger things from that. And so the distinction that we get from these two data structures, which if you paid attention in 161 and you've seen Dijkstra's algorithm, effectively this distinction is the same distinction that you have in Dijkstra's algorithm between things that you've discovered and things that you've finished, that you've done further exploration from them. So things in the table or chart are things that you know exist, that you know that there's a possible constituent there. Those things are then put in the agenda, and when you take them off the agenda, you then work out what you can do with them, like how can you explore further from this thing. Okay, and so in general, something can appear, you can find multiple ways of building something, so you could put something in the table once, and then you can find a different way of making a noun phrase from 2 to 5, and at that point, you can look at its current score in the agenda. If new way of making it has a better score, you update its score in the agenda and it'll drift towards the top of the priority queue. If the new way of making it is worse than the way that you made it before, you don't need to make any change. Okay, so that the general algorithm for agenda-based parsing is you have to initialize things in some way, so you need to put some items into your chart, such as the words and they're part of speech tags, and you have to have something on the agenda to start off with. And so you might start off with initializing the agenda with rules that can use parts of speech tags. And then the general algorithm is you take the best thing off the top of the agenda, you find all ways that you can locally explore around it. So how can you take that item from the agenda and sort of combine it into bigger things on either the left or the right? And that will lead you to build new, even bigger things, which you stick in the chart, and that will then give new tasks to the agenda. And this includes the unary rules. And then you kind of repeat over this loop of keeping on taking off the best thing from the agenda and exploring it. And then at some point you stop. And when you stop isn't when you've found a way of parsing the whole sentence over on this side, because you may yet find a better way of parsing the whole sentence. The right time to stop is when you pop from the agenda a way of parsing the whole sentence, because that means that you've found at that point what your system thinks is the best way of parsing the whole sentence. Okay. So that's the general framework of agenda-based parsing. If you think about it, if I don't specify anything more, it's just a general family of ways of doing parsing. And in fact, you can code up CKY parsing like this. I mean, I don't recommend you do so because it's just taking a fairly simple thing and making it more complex. But if you wanted to, you could code up CKY parsing as this kind of agenda-based parsing. The way that you do it is say that the score of an item is its size, and have the priority queue ordered so that small size is good. And so then the first things that came off the priority queue would be all the size 1 items, and then all the size 2 items, and then all the size 3 items, and you'd simulate doing CKY parsing. Okay, so what we want to do now, though, is to do less work than before. And so the idea is, well, maybe what we could do is use some of our probability ideas to work out how to do less work. And so the very simplest idea is to say, okay, when we build any item, we know what its score is, at least for that way of building it, right? That we've built a noun phrase in some way, we know the probability of that way of building a noun phrase. So let's use that probability as a goodness measure, and so explore forward from that. Okay, so we stick on the probability of an edge, and then what we're going to do is use that probability to order our agenda. And so that gives us a Dijkstra's algorithm, or uniform cost search in AI terms, where you're just ordering things by the probability of the part that you've already built. Okay, and so uniform cost parsing now, rather than being like CKY, where you order things by their span, now you're ordering things by what is their probability, so that you do all of the highest probability things, and then you start working out to building with lower probability things. And so this is, again, also easily, you can show that this is a provably correct algorithm, which will necessarily find the best parts of a sentence. And the essence of that algorithm proof, which I'll just give extremely briefly, is that because we have rules that are probabilities, and under the assumption that the probability of each rule is less than 1, i.e. there are at least a couple of rules that rewrite each non-terminal, then whenever you build something bigger, it has a smaller probability than something it's made out of. And therefore, because we put things in the agenda and take out the highest probability one first, we have to have built this before we built that. So if this is in the agenda, that must be in the agenda. And, well, by assumption, this has to have higher probability than that. Therefore, this has to come off the agenda first and be expanded. And so, therefore, we can guarantee that when we pop parts of when we pop a constituent that spans the entire sentence off the agenda, it has to be the highest probability way of parsing the entire sentence. And at that point, we can stop and guarantee that we found the best parse of the sentence. Okay, so here's just a little example of the difference. So here's a tiny little grammar of the kind that well, it's different to the one that I've used before, since this one is using noun-verb ambiguity. So this is people, fish, tanks. And it has an ambiguity because you can either have people, fish as a noun and tanks as a verb. You know, this is some new startup called people, fish. Or you can have fish as a verb and have people, fish, tanks. Yeah, it's another of my tortured attempts to make ambiguous sentences with very few words. And so that's a grammar that will find both of those parsers. And so then here in very small print that you can't read, but this will just give you the idea, this is the order of things that you build if you do CKY parsing. So you first of all build all the things of span 1 in each cell, 0, 1, 1 to 2, 2 to 3, then the things of span 2 in each cell, and then eventually you build the things of span 0 to 3 in each cell. Here on this side is the order of things in which you'd explore doing uniform cost search. And the important point to notice is here that the order in which things explore are mixed up because it does things in different orders. So it first of all does something from 0 to 1, but the next thing it does is from 1 to 2 because there's a high probability lexical rule, and so that's the next thing that comes off the agenda. And when it starts to see something promising, it starts here building a sentence from 0 to 2 long before it's built other one-span constituents that had lower probabilities. And by the time it's got to here, about 2/3 of the way down, it's built the sentence from 0 to 3 with the highest score, and it can stop. And so we've saved some work. So if you can see that green is then stuff that we don't have to do that we did with the CKY parser. sorry, I think I said that wrong. The green is the stuff that you did have to do, and the rest of the stuff is the stuff you avoided. Okay, so that seemed reasonably good in that example because I avoided, about a third of the work. In practice, doing uniform cost search just isn't much dice for doing parsing, and in general, people don't do it. And the reason for that is, if you think about it more for a moment, well, what do you explore in uniform cost search? You explore everything that's got high probability, but just because of the way probabilities work, when you kind of multiply probabilities, and the more that you multiply them, the smaller that they get, that it turns out that in these parse trees, almost everything small has higher probability than something big. That if you've got a 2-word constituent, it doesn't matter how bizarre it is, a PCFG is still going to give it higher probability than any 10-word constituent. I mean, that's not strictly a theorem, but, in practice, that's what happens, right? Almost everything small gets built. And so you can actually run this with a broad coverage tree bank PCFG of the kind that you built for the assignment, and it turns out that if you do uniform cost search, you save about 10% of the work. And somehow saving 10% of the work doesn't really seem enough motivation to work harder, in particular because the 10% of the work is normally at the cost of actually things running slower, simply because of the fact that you can write these tight for loops for CKY parsing. In practice, that tends to run much faster than a uniform cost search when you have to fiddle around with priority queues and data structures like that, which take longer. Okay, so if you want to pursue this game, you have to do something more than uniform cost search. And so you want to find some way of searching where you satisfy the goal of speed, that you're building the promising edges and not all of the unpromising edges. And so clearly the uniform cost search heuristic isn't enough to do that. And so preferably you'd then also like to build the edges in a good order. So for uniform cost search and some other forms of search, it has this property of correctness, that you can guarantee that you found the best solution according to your model. And that seems to be, in principle, a nice property to have, though it's a property that actually quite a bit of work in probabilistic parsing forgoes and instead settles with being able to find good structures most of the time. Okay, so for speeding up agenda-based parsers, one way of doing it is to say, do A-star parsing. So it's like A-star search, apart from done over our hypergraphs. And so that depends on having a good heuristic for the work still to be done. And so the idea is we can fix the problems with uniform cost search, where every little constituent is being built, by in some way saying, yeah, you've built a little constituent and its probability looks okay, but you've still got a lot of work up to do after that before you have a parse of the sentence, and that'll cost you, and so it's not actually such a promising thing to build. And that's something I explored with Dan Klein. But in practice, this hasn't been used much. Most of the time, what people actually use is heuristic searches. One of the well-known methods is actually one by Eugene Charniak, which is used in his parser, which he calls best first search. But the important thing to remember is best first search isn't. It's best first search in Eugene Charniak's sense means think it looks best first search, and that there's absolutely no guarantee that actually that the best thing comes out at the end. Okay, I'm going to skip past and not actually explain all the details of the A-star search, but I'll just show you this graph, which gives you a sense as to why it's hard to win doing A-star search and why it's not that widely used in practice. So what this is showing is we were wanting to come up with A-star estimates for the work still to be done. So the idea is that you've built a noun phrase from positions 5 to 10 inside a 20-word sentence. And what you want to do is come up with an estimate of how much work that you'll have to do to parse the rest of the sentence, i.e. the stuff from 0 to 5 and the stuff from 10 to 20, and the cost of a rule that connects it together with what your noun phrase from 5 to 10. So somehow you have to estimate the cost still to be done to finish parsing the sentence. And so that's what we tried to do, and we came up with a range of estimates. And so the simplest estimate here, S, was just saying all you know is that there's 5 words to the left and 10 words to the right, which you have to incorporate into the parse of a sentence. And then we came up with successively more refined estimates. So for SX, you also know, and the constituent that you need to combine it with as a noun phrase. For SXR, you know, and the constituent and the thing to the right of the constituent that you've built is a preposition. And then for B, it adds in several more pieces of information. And what you can see is that as we kind of add in more information and come up with a better estimate, our estimates improve. We get a tighter estimate, and so that the minimum possible cost, sorry, I should explain first. The axis here is in log probability, so that's why it's negative scores. So the maximum probability completion is going down because we're getting a tighter estimate because we're incorporating more information about the context. And that means on average, the probability cost of completing the rest of the sentence the probability of completing the rest of the sentence will be lower, which is being shown here as a log probability as a lower number. So our estimates are getting better, but there's a huge problem, which is this. Looking at this black line here. This black line is, let's take the actual sentences that we're meant to parse and the actual constituents that we build, and what estimate we came up for the outside work is here, and the actual probability cost of parsing the rest of the sentence, the average probability cost is this black line. And so what you see is that although our estimates were getting better, and because this is on a log scale, they're getting better by several orders of magnitude better, that the crucial thing to note is that all of these lines are basically parallel at this slope, whereas the real cost of completing the rest of the sentence is going down here at this fundamentally different slope. And if you think about it, it's kind of obvious why that is. That if you're doing A-star search, all of those theorems you go through in 221 is that your heuristic has to be optimistic, in that the heuristic has to always underestimate the true cost of doing the rest of the work. And so that means necessarily in every place, rather than saying, well, on average to parse up 5 words like that will cost me probability 10 to the minus 7, you always have to say, well, if they're the best possible words in the best possible configuration, the cost of including them will only be 10 to the minus 3, and use that as your estimate. So you're always making, in every possible case, the most optimistic possible assumptions about what else remains. And as we come up with better estimates up here, our estimates get closer. So if the outside span is extremely small, like there are only kind of 2 or 4 words left to parse, our estimates can start getting very close to the truth. Because we can essentially build our estimates taking account of the words that are outside of what we built. But if the span is large, we can't do that because, well, the only way we could build an accurate outside estimate is actually by parsing the rest of the sentence and finding out how much it costs to parse the rest of the sentence. And, well, it doesn't work if your A-star heuristic costs you as much time to compute as actually doing the parsing. Then you don't get any gains. You have to have a way of computing the A-star heuristic that's relatively cheap. And the way that we did that was we pre-computed A-star heuristics exhaustively for configurations that were conditioned on only a few bits of information, the kind of things that I talked about. Okay, so I guess so A-star search is kind of cool, but the lot to take away from this is it's never really going to get you a really fast parser. And I mean, there is kind of there an interesting conflict if you're kind of thinking in statistical terms, that A-star search is always taking the very best possible outcome that could possibly happen, where it's really much more statistical thinking to actually be wondering, well, what's the average behavior that should be happening? And so that's exactly what Charniak's best first parsing does. So Charniak's best first parsing is that you estimate for an item about how much you think it'll cost you to parse the rest of the sentence, where the about how much it will cost you to parse the rest of the sentence is trying to come up with an accurate estimate of this black line. And Charniak does a good job. He comes up with an accurate estimate of that black line. And so most of the time, his stuff works really great. Now, if he messes up, if he explores the wrong thing first, so he finds a way of building a noun phrase from 5 to 10 and then starts building things on top of that, but then somehow he messed up and later discovers that there was a better way to build that noun phrase from 5 to 10, then the algorithm's got a problem. You then have to go back and redo all the work that you've built on top of that noun phrase from 5 to 10, because all of that work is now wrong because you've found a better way of building that noun phrase. And so you lose the nice property of Dijkstra's algorithm or A-star algorithms, where you're guaranteed to find the optimal method of doing things without repeat work. But in practice, the algorithm works extremely well because it's really good at finding the right way to make edges and relatively infrequently needs to do that kind of fix-up. Okay. So here are just sort of a summary of a few parsers. So people have done different things. So we use this A-star search, which I've now been knocking. Collins and his parser effectively used a kind of a mix between agenda-based parsing and beam parsing. So it was agenda-based in what to explore, but then simultaneously also used beams that limited the amount of things that you explored over any particular span. And then Charniak used this idea of his inadmissible heuristic that I've just talked about. And actually, of the three, his way of doing it is the faster, because his inadmissible heuristics are actually really good in practice at coming up with good estimates of the cost of things. One other idea that's been explored lately in parsing that's given people a lot of speed up goes in a different direction. And the idea here is that you can guide the work for the parser to do by parsing first with one or more different grammars that are coarser grammars but can nevertheless tell you what's useful to explore. So the idea here is, well, you know, for your grammars for the assignment, you were asked to do parent annotation. So you had categories like VP under an S or VP under an NP and things like that. Well, that was good for improving parse accuracy, but the problem is doing that actually causes your parser to go much slower because you've now got a lot more symbols in your grammar. And remember, there's also a grammar constant term in the parsing time, and so you're slowing down based on the factor that's roughly g cubed in the number of grammar symbols. So what if you first of all parse with a very small grammar that has few symbols in it? So like a basic PCFG, where you just throw away all these refinements of lexicalization, subcategorization, and work out the things that you can build that are kind of likely in that basic PCFG. They'll still probably be good things to explore in the bigger space. And so this has been used very successfully by a couple of recent parsers, Charniak and Johnson's and Petrov and Klein's. And then here is a little animation of this from Petrov and Klein, which is showing through successive refinements of the grammar which things are being explored. So for the coarsest grammar, I don't know if I show that again. For the coarsest grammar, they explore everything. Then they continue to explore in successive phases only the things that have substantial probability in the early phase. So for their most refined grammar, that they're actually exploring very few cells in the chart because they have a very good idea of which ones are likely to be in the final parse. Okay. So that's me having rushed through parsing as search, and so now on to the final two topics, which are dependency parsing and then discriminative parsing. Pause for breath. Is everyone happy as parsing with search? Okay. Yeah, dependency grammar. So this is a change of tack, though it then does connect up again. You know, what we've mainly worked on and what modern American linguistics and modern American computational linguistics has mainly worked on is constituency parsing. Things like noun phrases, verb phrases, building these constituents, putting them together with context-free grammar rules. It turns out that idea of context-free grammars and doing things with constituency is actually just a really new idea. So the idea of constituency was basically invented in the 1920s by a British guy. I think his name might have been Wells. I forget it now. But around 1920s, it started to be used in some early American linguistics. And then it was only in the 1950s that Chomsky came up with the Chomsky hierarchy and the idea of context-free grammars. So overall, the idea only has sort of about 80 years of, well, 90 now, I guess, 90 years of history and about 60 in a formalized fashion. So in terms of kind of the whole history of grammar, what people have used for millennia to think of the structure of sentences isn't that. It's instead the idea of dependency structure. And I'll just show a picture first. The idea of dependency structure is what you're doing is for words, you're saying what their dependents are. So here's acquired, and so this is a dependent of it, the subject. This is a dependent of it, 30% of American City, the object, and here's another dependent of it in March. And then for each of these, Shaw Publishing, so this is the kind of the head word of the dependent, and it's got its own dependent, which is Shaw. So that's the idea of a dependency grammar representation. It used to be used in American schools. So up until, I know, was it the 50s or 60s, all American school children were taught diagramming sentences. Probably none of you, has anyone ever seen diagramming? Yes! Okay. Some people still got taught diagramming sentences, at least a little. Right, so diagramming sentences was a notation that's, I don't actually know the full history of it, but I mean, it got ingrained in American education and it was kind of uniformly taught in the first half of the 20th century as a way of sort of understanding sentence structure, though sort of with some of the modern reforms, a lot of people never see it these days. But diagramming sentences, it's a dependency representation. It's got its own funny ways of drawing the lines at different angles to represent different things, but it's a dependency representation. This kind of way of drawing kind of arrows is what you most commonly see as dependencies. But the one caution I should immediately give is half of people draw the arrows one way and the other half draw the arrows the other way. So you kind of have to just look and see whether the person is drawing the arrows from heads to dependents or dependents to heads, because both of them are actually quite commonly used. But hopefully they're at least consistent in any one diagram. Okay, so huge history of dependency grammar. So normally the person recognized as first producing a precise grammatical description of a language is Panini, who worked on Sanskrit. And, you know, he worked all the way from phonology up through syntax, but his syntax is a dependency grammar. Arabic grammarians working around the 5th to the 9th century AD, they all used dependency grammar. Then, I mean, if you look at the Chinese, Japanese grammatical tradition, dependency grammar. and, you know, early 20th century American schools, dependency grammar. So basically, everything is dependency grammar. The sort of modern formalized dependency grammar is often traced to Tesnier's work, which is then from the late 50s, around the same time as Chomsky's work. Because of this, actually dependency grammar was some of the first work that was explored in computational linguistics too, even in the US. So all this kind of early Soviet work was definitely dependency grammar, but also in the US, David Hayes was one of the sort of first computational linguists in the United States and one of the founders of the Association of Computational Linguistics. And he wrote this 1962 dependency parser for English, which is sort of around the years when some of these other algorithms like CKY were being invented, right? We had those dates of 1960 for John Koch and 65 for Kasami and Younger. Okay, so that's the history. Oh yeah, the other footnote is, normally when you do dependency parsing, you sort of put this fake extra thing here, which can either be on the left or the right, which has some word like called something like the root or the wall or something, and it just kind of makes the algorithm more straightforward, because if you do that, you have the property that every real word is the dependent of something. And so you have this definite place to start from. And so what you want to do is find what is the dependent of this. That's the head of the whole sentence. And then you want to work down and then recursively find heads downward. Okay. So how do these two things relate to each other? And there's sort of a straightforward answer to that, though, with a few little gotchas. So officially, a CFG has no notion of a head. So, you know, you just have, you know, A rewrites as BCD, no notion of a head. So if you're in that space, there isn't any real equivalence that you can draw between dependency grammars and CFGs. But in practice, for linguistic purposes, that's kind of not what anybody uses. That people use, and all of our algorithms for lexicalized parsing, for example, used a notion of headed CFGs, that more or less informally, people know what the head is, so that if you have a verb phrase going to a verb, a noun phrase, and a prepositional phrase, in people's heads and in their imagination from the symbol names, the verb is the head of the rule. And so you could formalize that and say, well, let's have a formalism of a headed CFG in which in each rewrite rule, you're marking one of the things on the right-hand side as the head of that rule. And so that kind of gets you a little bit closer to a dependency grammar. But there's still one other crucial difference. So that in a dependency grammar, like in the picture back here, you have a head and then all its dependents. And all its dependents are equivalent. That you can't have the notion that some of the dependents are kind of privileged in grouping with it before others. In particular, very standardly in constituency representations, you have this idea of a verb phrase, acquired 30% of American City, which is made as a phrase before you can combine it with Shaw Publishing. So you have these intermediate constituents like verb phrase, where a word has taken some of its dependents, but not all of its dependents. And so that's an idea that you can't represent in dependency grammar. So the isomorphism that you get is that if you have headed phrase structure rules where there's kind of only one level of projection, so that you go from a word to its phrase, like verb to verb phrase, and all the dependents of the verb are contained inside the verb phrase. So there's a head marked and one level of projection. Then what you get is actually isomorphic to a dependency grammar. And it takes a moment to see that because it's represented very differently, but it ends up isomorphic. And the idea of how to see that is that here's a word, and here is the head word of its dependent. And to find out what the size of this phrase is, what you can then do is just follow dependencies recursively. So starting from the head word of this dependent, you kind of follow recursively all dependents and get the closure, which here is just Shaw Publishing. And that's equivalent to that phrase being something that the verb phrase acquired rewrites as this phrase, and then some other phrases over here. So similarly over here, from acquired, you go to here, which at least in this example is marked as the head, and then you could recursively follow along and find the other words, and you have this implicit phrase of 30% of American city. And so the constituents are implicitly represented, and if they're done like this, so that none of these dependency lines cross, they are mappable onto a phrase structure tree. Okay. And we've already talked about propagating head words. Okay, well, no, what was I going to say here? Okay, so one way of getting dependencies is, that if what you have here is a pen tree, pen trees don't directly show dependency relations, but you can kind of reconstruct a form of dependency relations where what you do is you have some rules that say what the head of a phrase is, so the VBD is the head of the verb phrase, and then you propagate the heads just as we did for lexicalized parsing, so this is VP announced. And then what you do is you flatten things a little and turn them into dependency relations. So here we have announced yesterday and announced his resignation and announced, John Smith announced, so that you're taking the pairs of things that you found in the phrase structure tree here of announced resignation, announced yesterday, and turning those into the dependencies. And if you do that in the most obvious way, you just get dependencies between words, though some work that's exploited the Penn tree bank and tried to do dependency parsing has then actually typed these dependencies by naming them after the phrase structure rule that they're associated with. So announced his resignation, the type of this dependency is named a VP, rewriting as a VBD NP dependency. And so that gives the kind of a name for the dependency based on phrase structure. Okay. But if we have those kind of dependency representations, we can then directly say, well, let's go about doing dependency parsing. And if we think of those kind of words with arrows between them, representations, that it seems like there are three basic ideas that we can use for dependency parsing. So the first one is the kind of obvious one that we've talked about before. It's this bilexical information. So is dependence a reasonable subject of the verb tend? Is tend fall, is this a reasonable verb complement of tend? In string, is that a reasonable bilexical dependency? So bilexical dependencies are very directly represented in dependency relations, and their probability is a very obvious thing to use for dependency parsing. It seems like there are two other key ideas that you want to represent for dependency parsing. One is the distance of dependencies. So what this picture here is meant to be showing in a comical way is that it turns out that most dependencies are very local. So that here's the subject dependence, and it's got its own dependence, and they appear right next to it. Tend to fall near it. Tend has this dependent and then a dependent here, and there are various other words. The dependencies are all close by. They're all close by. You have to have occasionally longer distance dependencies. So from dependence to tend is slightly longer distance because there's this stuff coming in the middle. But the vast majority of dependents are local. So you get an enormous amount of information in dependency parsing by having a strong preference to local dependencies. And then the third feature is valence, where valence is like Collins's subcategorization features, that you want to have an idea of how many dependents a word should have. So here we have the verb tend, and it's got 2 dependents. That's good for a lot of verbs. A lot of verbs, it's bad news if they have 0 dependents. It's good news if they have 1 or 2 dependents. Some verbs, particular verbs, will take 3 or 4 sometimes, but some verbs won't. Here we've got the word the. The doesn't have any dependents. That's what you'd expect for the word the, no dependents. Here you've got string with 1 dependent. That's typical. Preposition in, you know that you've messed up pretty much if a preposition doesn't have 2 dependents. It should have 1 dependent for its prepositional object, and it should have another dependent for what it's modifying. So there's a lot of information in counting the number of dependencies things have. And so it's effectively those 3 sources of information that by and large dependency parsers are built around. Okay. So this is the kind of basic generative probabilistic model that people use for dependency grammars. You start at the wall, you generate the head word of the whole sentence based on a probability distribution. You then gradually generate its children to the left side, so you have some kind of Markov model style generation process where you generate children to the left using a probability distribution, and then you have a chance of stopping, and at some point you stop. You then generate children to the right with some kind of Markov model with the stopping probability when you found all of the right side children. Then for each of those, you recurse, and you say, for each of those words, let me generate its left children, let me generate its right children, and that will stop. And you effectively bottom out when you get down to words or parts of speech. You bottom out when you get to parts of speech which necessarily have no left children and no right children, and then you're done. So there's a straightforward parameterization of a probabilistic dependency grammar. And this is showing the second round of the recursion. Okay, and then you return it. Okay. So that's how you generate a sentence. How do you parse a sentence? I mean, the first idea that might pop into your head is, okay, well, we've got the words, and so the words are things. And then what we could do is we could combine words. So let's say that 2 is the object of takes, so we can combine these things, equivalent to putting that arrow there, and build this constituent takes 2, which is headed by takes, and then we'll kind of repeat over 2 tango. We can combine them as a dependency and build a constituent headed by 2, and then we can combine those, and we can say 2 tango is a kind of another infinitive dependent of takes, so we've built a constituent like that, and we continue up to the top of the sentence. But the problem if you do this, and this is the same thing that I mentioned with lexicalized parsing, this algorithm looks very obvious, and it seems like it can't do any harm. But if you do this algorithm, you've ended up with an n to the 5th algorithm, again, for doing parsing. And the reason for that is that in general, once you get into bigger sentences, it isn't actually true in this example, but in general, once you get to bigger sentences, the head of a constituent that you've built will be somewhere in the middle of the constituent. And that will be true for both this one here and that one there. You have both their left extent, their right extent, and you have a head that's in the middle of them. And so you need to keep track of the extents and where the head is in the middle, which in general means that your rule for building things looks like this. You've got a left extent, a head, a right extent, which has to be the left extent of the next thing, a head of the right thing, and a right extent, which you're combining together to produce a new thing. And because you're keeping these 5 indexes into a sentence, that you end up with an O(n) to the 5th algorithm. So that's bad news, and it seems like dependency parsing shouldn't actually be that complex because we're not actually making inherent use of phrasal constituents anymore. And it turns out that it isn't that complex, and you can do dependency parsing in cubic time in the length of the sentence. And that's something that's been worked on recently, and this is shown in the work of Jason Eisner and Giorgio Satta. And so they present a clever algorithm as to how you can go about thinking about doing dependency parsing to make it a cubic algorithm. And these same ideas can be extended into lexicalized parsing, as I mentioned earlier. And so I'll just explain this briefly. I'll probably explain it so quickly. I think this is something that you have to stare at for half an hour and actually work it out in your own head before it can possibly make sense. So I think there's sort of probably little chance I could explain it well enough that it will make sense, and certainly won't today. But here very quickly is the idea of it. The crucial idea of it is you're going to make these different kind of parse items, the trapezoids. And so what the trapezoids are is that the trapezoids are going to be, say that in your parse you can make something where on this side, the tall side is the head, on the low side is the dependent, and this trapezoid has the property that it contains all of the right dependents of the dependent and all of the left dependents, all the prior left dependents of the head before this one in such a way as they touch in the middle. So what's the intuition here? The intuition here was on the last diagram. The reason why we were messed up was that the heads were in the middle of things. And so if the heads are in the middle of things, we kind of have these extra two indices, and it gets turned into an n to the fifth algorithm. So what if we did some freaky stuff, and instead what we did was we kind of made this piece here into a trapezoid, where the trapezoid is saying it's got all of the dependents, oh sorry, this is the child, so if I call this parent-child, it's saying it's got all of the left dependents on this side, it's got some right dependents on this side, and these right dependents stretch until where left dependence of this word begins. And if I cut out that piece and call it a trapezoid, then I'll have constructed something where the head word and the dependent were on the edges of it rather than stuck in the middle. And that way I'm going to get rid of needing to have these two extra indices. Okay, and so that's what the algorithm does. So you have these two data structures. Okay, so you have triangles. So on triangles, the tall side is the head, and these, down on the other side, you've got dependents. And the dependents that you've identified are guaranteed to be complete in that they've found all of their own dependents. And then you have trapezoids, where trapezoids have the head on the tall side, a dependent on the low side. All of the left children of the dependent have been found, and they can span out to touch some right dependents of the head, but it's still unspecified what's out on this side. Out on this side, there may be other stuff, and this other stuff might be further dependence of the dependent, or it might be further dependence of the head. Okay, so then this is the algorithm when we do that. Okay, we start with the same sentence. We start off, because these are just words, as saying these are completed triangles for the various parts of speech that we can build. Things that don't have any more dependence on the left and don't have any more dependence on the right. So then we can start building trapezoids. Okay, so we can say, okay, I can make a trapezoid by combining these two triangles. This is the head, this is a dependent, and these two, since these two triangles touch, there are no words in between them, I'm able to make a trapezoid here. Okay, I can make another trapezoid there. Okay, because these two triangles touch, head dependent, make a trapezoid. And I can then keep on going. Here's a trapezoid I can make to tango. At this point, I can say, okay, this thing has no left dependence, so I can build a complete triangle here. Here's the head, no more dependence to be found on the left-hand side. On the right-hand, I can also make that triangle on the right-hand side, but then I can also make more trapezoids by combining up. And so I do this alternation where I build triangles and trapezoids. And the crucial thing to notice is that because both the triangles and the trapezoids have their stuff at the edges of them, that the number of things that I can build by combining trapezoids or combining triangles, that's all O(n) cubed again, because when I'm putting things together, I'm putting together two triangles to make a trapezoid, n cubed, or else I'm putting together a trapezoid and a triangle, n cubed. And so I'm doing these n cubed operations, and so I end up with an n cubed parser. Hopefully that is just enough to leave you confused, but thinking that there might be a neat algorithm here if you spend enough time to understand it. Okay. Yeah, so very quickly then for the rest of this. So when people do dependency parsing, the way people normally score dependency parsing is just with dependency accuracy. So if these are the dependents and their labels, you just sort of have the gold answers, the guessed answers, and you sort of say what percentage of them are right as dependent. So that's a head position, a dependent position, and optionally a label, and you get an accuracy measure. And the reason that that seems fine to do is that the number of dependencies is just the number of words in the sentence. So if you put in a root, so every word is a dependent, it's a dependent of one thing, so you're just making number of words of this in the sentence dependency decisions, and so it's sort of fine to score by accuracy. There's no reason to do F measure. Okay. So there's been a lot of work recently in dependency parsing again. In particular, there was this Connell competition for a couple of years doing a dependency parser. One of the big attributes of dependency parsers is that they can be really fast. They can largely be really fast because they avoid the large grammar constant of PCFG parsers. But, current results is that dependency parsers are typically an order of magnitude faster than good PCFG-based parsers. So if essentially what you want is a dependency-like representation and you just want to get it quickly, you're really better off using a dependency parser. And so lots of work has used the dependency parser. And for a lot of kind of meaning extraction applications, dependency representations actually seem much easier and more like the structure that you want to deal with for getting the meanings of things out. So one well-known recent dependency parser is Ryan McDonald's dependency parser, which there are various papers on. I mean, an interesting question to ask is, how good are these dependency parsers? Are they as good as constituency parsers? And the answer to that seems to be almost, but not quite. Well, it's kind of hard to compare the two kinds of parsers based on getting constituency right, because the dependency parser doesn't label constituents. It doesn't say this is a noun phrase, this is a verb phrase. You could measure unlabeled constituency and just say where did it propose constituents. But the easiest way to evaluate them seems to be to say, since our lexicalized PCFGs are implicitly headed anyway, why don't we just evaluate their dependency scores and see how they compare on dependency scores? And so if you do that, Ryan McDonald's dependency parser had 90.9% dependency accuracy. The Collins 2000 parser had 91.4% dependency accuracy. So it is actually slightly better. I think there's something about the constituency parameterization which is actually a little bit useful to parsers, but that's not very big difference when it comes down to it. And the next thing that Ryan McDonald immediately did was used scores from Collins's parser as an extra feature inside his dependency parser, and then he was able to get 92.2% by taking advantage of it as a feature in his parser. Okay. Maybe I'll skip that. Okay, so for the last few minutes, I then just wanted to say a little bit about discriminative parsing, just to give a flavor of that. So we talked for several lectures in the kind of information extraction sequence model part about how let's build discriminative models of these CMM, MEMMs much better than building generative models. And so kind of the obvious question is to ask is, well, why not do that for parsing as well? Shouldn't it be better for exactly the same reasons that it's better for doing sequence models and information extraction? And the answer to that is yes, but that the yes, it is better is certainly the case. On the other hand, it's kind of a complex enough thing to do that it's still not yet really kind of real, that most of the parsers that most people are using most of the time are still generative lexicalized PCFG parsers. So that kind of contrasts sharply with the space of sequence models, where these days, for most tasks, people don't use generative models like HMMs. They use discriminative models, whether SVM-based or maximum entropy-based like we did. That's just not the case for parsing. Okay, so if you want to do parsing, you know, in the abstract, it's discriminative parsing. It's exactly the same problem, right? We've got a set of IID samples where we have the input X, which is a sentence, and our class Y that we want to assign using our discriminative function. The problem is that the class of a sentence is a parse tree, which means that you need to build a model over and large, well actually infinite number of classes. You've no longer just got, let me label this as person, location, or other, right? You now are trying to label over an infinite number of parse trees. That might appear as if it's just impossible, but it's not impossible. And the reason it's not impossible is we had features, right? The way I defined things, that the features were f of x, y. They were a feature of the observed data and the class that you wanted to assign. So what you can do is have features that are sensitive to bits of the parse tree. Like the feature can say, the sentence has the word in it, and somewhere in the parse tree there's a prepositional phrase. That's a possible feature. And so the features can check bits of parsers. And so therefore you can give a score to a parse by having features that look at bits of the parse. And so effectively you can do discriminative techniques over this infinite category space of parse trees. Okay, and here's my motivating example, which I borrow from a similar example from Mark Johnson, as to where generative parsers go wrong and why being able to do discriminative parsing is actually a really good idea. So let's just look at this example for a minute. So here's this is my training tree bank. So I've got a training corpus of 108 imperative sentences, 100 of which are eat, and 6 of which are eat rice with chopsticks, and 2 of which are eat rice with chopsticks, where rice with chopsticks is now an NP. So these 6 have the VP attachment, and these 2 have the noun phrase attachment of rice with chopsticks. I guess this is really bad in China, right? That you put chopsticks into rice for dead people, and so you don't want to get that parse. Okay, now here's the question. If this is my training tree bank and I train a PCFG and then I give it the sentence to parse of eat rice with chopsticks, what parse will my PCFG return? I mean, if you just look at it for a fraction of a moment, you think, well, of course it should return this one because we got this 6 times, whereas we only got that one twice. But the fact of the matter is that's not what you get out. And the reason that you don't get that out is because of this. And this is sort of a really kind of a weird thing that it takes a minute to wrap your brain around as to how PCFGs end up acting. That you get this really weird effect that because these trees are in the grammar, in a PCFG, that actually affects your choice over here. Whereas it seems intuitively like this should just have nothing to do with your choice over here. Your choice over here should be based on this happens 3 times as often as that, therefore you should choose this parse for eat rice with chopsticks. But why it goes wrong is if you look at these sentences, half the constituents are the same, right? So both of them have a VP goes to VNP, VP goes to VNP. Both of them have a PP goes to PNP here. And so the differences between the parsers are this one has a VP goes to VPPP, and this one has an NP goes to NPPP. Now, what happens when you make a PCFG? Well, for a PCFG, it says, well, let's look at ways to rewrite a verb phrase. There's 108 VP goes to Vs. There are 6 VP. Right. No, let me get this right. There are 8 VP goes to VNPs, 6 here and 2 there, and there are precisely 6 VP goes to VPPP. So if you add that all up, you had 108 plus 8 plus 6, 122. The probability of this rule is 6 over 122. Small. Whereas for NP, right, we have these NP rewrites here, of which there are 6 each. We have 2 more of each of them here, so there are 8 each of them. And then we have 2 instances of NP goes to NPPP. So that there are 12 and 4. There are 18 rewrites of NP, and 2 of them are to NPPP. So the probability of this rule is 1/9. And so the only difference between these PCFG structures is that this one has the VP goes to VPPP rule, and this one has the NP goes to NPPP rule. And the probability of this rule, 1/9, comes out as higher than the probability of this rule because of all these damn constituents over here. And so the PCFG parser will actually return this structure if given that sentence to parse from the construction of the PCFG. That seems wonky. And so that's precisely what you can fix if you do discriminative parsing, that a discriminative parser can effectively learn that what it needs to do is be down-weighting the NP goes to NPPP rule and up-weighting the VP goes to VPPP rule so that it'll get this parse choice correct. And it'll still get the choice of every other parse correct at the same time. So it's just kind of like my example with traffic lights, that you can change the scores of things in such a way that you can make better discrimination decisions, whereas a PCFG will get it wrong. Okay. So staring at that example and convincing yourself that is true, that is my main concept on understanding that there's something to this discriminative parsing idea. I mean, the practice, there's then all the usual stuff I talked about before that, you can put in general kinds of features and stuff like that. Let me skip right to, okay, so how can you do discriminative parsing? There are at least a couple of ways that you can do it, or at least 3. I mean, one way is that you can say, well, if I've got something like a parser, I'm making a sequence of choices, shift reducers, building constituents. I can make each of those choices discriminatively. Or else you can say, well, surely I can write a dynamic program which will do parsing and use discriminative scoring everywhere. Or a third choice is you can say, well, let me parse with a generative parser and get out an n-best list, and then I'll re-rank it using a discriminative algorithm, because then I'll only have 15 parse candidates to deal with rather than having to deal with this infinite category space. And all of those methods have been used. So an early parser was Ratnapaki's, which was a shift-reduced parser that did discriminative estimation of which decisions to make. It didn't actually work so well. It actually, it worked okay, but it worked a little bit worse than the best generative parsers in around the same year, around 97, 98. And I think the reason for that is that if you just try and do discrimination at the level of individual parse decisions, you make effectively can make very bad decisions because of the structure of the model that you're using, if you think about it as a model class, because you're kind of making decisions that are independent of the future if you make discriminative decisions. You can do dynamic program generative discriminative parsers. This is something that people are working actively on at the moment. I think Ben Taskar's here. Well, actually, it wasn't quite the first. It was one of the first that did that. The problem with Ben Taskar's one was it took him kind of 3 months to train a model that could parse 15-word sentences. Discriminative estimation, really, really expensive. People have continued working on that, and it's sort of starting to be that with better algorithms, better algorithms and more distribution over multiple machines, it's starting to get to the point where you could do it more sensibly. The kind of current state of the art is, nevertheless, is the Charniak-Johnson parser, where it's then using a maximum entropy discriminative re-ranker on the 50 best that comes out of the Charniak parser. And the other advantage of doing re-ranking is if you do re-ranking, it's very easy to write global features that look at anything of interest and say whether it's a good or bad parse. And so you can have features that look at big things, like do these two conjoined 10-word phrases look sensible? Whereas if you're going to stick to dynamic programming, you kind of have to have local features. So his results, or their results now, are that they can get 91% F1 on sentences of all lengths, which is equivalent to 92 point something, looking just at sentences up to 40 words. So that's the current state of the art of parsing, as this sort of mixed generative discriminative re-rank model. Okay, and I'll stop there and say that's the end of parsing, and then go on to semantics and meaning next time.